as it says, is a scalable metamodeling methodology that uses stacking to combine many models in a neural network type of architecture of multiple levels. Now, to break this down and make it a bit easier, this is this is scalable because you can run many models in parallel. So you can run many machine learning models in parallel, and the more computing power you have, the more cores you have, the quicker the fitting will be. It utilizes a technique called stack generalization to combine all the different models, and we will discuss about this later. For now, let's just leave it here. And as you can see also a bit in this graph, the way it combines the different models, it looks a bit like a neural network. So again, we will see more details about it later on, but the basic idea is that you can combine models in various stages, and we will see what this means in a little while. So why would you think, why would this interest you? As a technique successful in the past, me and my team, in order to win machine learning competitions. And this is a graph from a popular Kaggle challenge called, I think, Truly Native. It was organized by a company called Dato, that they also have a predictive modeling software. And you had to predict if a website will contain certain information. So it's just text data. We generated 2 different data sets, and then we built various machine learning models. Then we used the predictions of these models and applied StackNet in order to meta-model them and get to a much better prediction, similar to a neural network. And although maybe we wouldn't need that 4th layer, we definitely need it until layer 3 in order to win these competitions. So there you go. I mean, if you're after exhausting all the information within your data in regards to predicting something, then this is a good technique to do that, because it goes really deep. And it was organized from home site. This was an endurance competition, and we again pretty much used the same framework. We built various data sets, we built many models, we used these predictions of these models in order to feed them to a 3-layer architecture of meta modeling in order to get the best prediction. I'm suspecting, again, we didn't need that 3rd layer, but we probably definitely needed the 2nd in order to win. So there you go. I mean, if you were really after in getting a very, very, very competitive score, then this is a tool where you can use to get that. Now, so far, this may seem a bit complicated, and I'm not sure what the background of people is, so I will try to give you a naive example about what is metamodeling. This example is literally very naive, so it's I'm only using it for explanatory purposes, in order, like for everyone to get comfortable with this definition before we move forward. So let's assume we have 3 kids, LR, SVM, KNN, and they argue about a physics question. So they try to find which one is the right answer. So LR would say 13, SVM says, no, I think the answer is 18, KNN says, I think the answer is 11. So they try to work it out. They cannot convince one another, so they decide to do a democratic thing and take an average and say the answer in this case is 14. So I want you to interpret the kids in this scenario as models. So they have some input data, which is a question about physics, and the outputs and predictions. And the algorithm is unique in its case, so the way they get to the answer is different. And they hope they can get to a better answer by combining the different predictions, by combining the different outputs. And this is a very simple form of ensembling. So ensembling in this case means combining models. But how would that look if we wanted to use a meta model? Who is overseeing this discussion, and she decides to step in. Let's say her name is Miss DL, and she's a maths teacher, and she says, actually, I don't know what the physics question was, nor I know physics myself, but what I do know is the children. I know them quite well. I've been teaching them for many years. I know their strengths, their weaknesses, and I know SVM is really good in physics. Her father also works in the Physics Institute of Excellence. So I'm very keen to put much higher weight on SVM's prediction. So what we do here is we introduce a higher authority that without knowing the input data, you see, she doesn't know the question, but she's very likely to be able to give a better estimate because she knows the strengths and weaknesses of the lower level models, in this case, the students. And she's able to give a different prediction than the average that hopefully is better. And this is how meta modeling works. This is the basic notion, how we can use a model that tries to learn when the models makes errors and tries to find the best way to combine them, to get a better prediction. Now we can make this a bit more complicated and say that Mr. RF also joins this little party, and he's also a physics teacher himself. He didn't hear the question, but he also knows the children, and he has been doing secret lessons to LR, and he believes that he couldn't be that far off. He believes that actually he's underestimated by Miss DL, and he's more keen to say the answer is more likely to be around 16. Now again, they could try and take an average, or in order to get a better prediction, or we can introduce a second layer of model. In this master, and the headmaster who knows his teachers quite well, he's more likely to trust, or let's say more keen to trust his physics teacher. Therefore, he thinks the answer is 16.2. And again, the basic idea is that the more, by introducing a higher level authority, you can get better predictions without actually revisiting the input data. So the headmaster has no idea what the question was, what the children were fighting about, but he knows the models at the lowest stage of him in order to, and he tries to give a better estimate. So this is the basic idea of meta modeling. Here I explain to you what you can get theoretically by adding a different layer of predictions, and I show it to you that, let's say, how it will look like if we were to go up to second level. And now we will go more to the technicalities. So this was more like a naive explanation of meta modeling. I mentioned briefly before that we use a technique called stacking or stack generalization in order to combine the different models. So this is a technique introduced by Wolpert in 1992, and it consists of several stages. So let's assume we have one data set or two data sets. We either have one that we divided into two parts, or we have two parts already. It doesn't matter. So we have two data sets. We can call the first one train, the second one validation. what we do is we take the first data set and we fit various models. So various machine learning models like regression, random forest, it doesn't matter what it is. And then we use these models and we make predictions to the second part. Now we take all these predictions, we put them together, and we form a new data set. And if we know the target variable of this data set, then we feed a new model with these predictions as inputs and with the target variable for that validation set as the main target variable. This is stack generalization. In order to illustrate this better, consider the following animation. So let's say we have three to xn, and you have a target variable y that you try to predict. Now for dataset A and dataset B, we know this y variable, but in C we don't know it. We want to predict it. So how are we going to use stack generalization to predict this y column in C? What we're going to do first is we are going to train an algorithm on A, and we are going to make predictions for B and C. Now we will take these predictions for B and C and we will create two new datasets, one for B and one for C. Let's call them B1, C1. B1 holds the predictions for the B dataset, C1 holds the predictions for the C dataset from an algorithm trained from the A dataset. And now we're going to do this again. We're going to take a new algorithm, we stack or we put these predictions in the B1 and C1 dataset. And you can see where the word stacking refers to, because each column gets appended, each prediction gets appended next to each other. And now let's say we do this again. So now we have constructed two different data sets. For B1, we know the target variable because we knew the target variable in the B data set, but we still don't know it for C. We tried to predict it. So what we're going to do now is we are going to use the newly formed data sets and train one last algorithm on B1 and make predictions for C1. And this is basically how you can use stacking or stack generalization. It's the same in order to make predictions for a test data set. So it requires to have another data set to make predictions, and then you use this data set to fit one last model. This is how it works. It has been very successful to combine hundreds of different models. And this is, I think, the most preferred technique I've seen in predictive modeling competitions. Now, let's try to think of StackNet a bit differently. I mentioned that this is a multi-layer architecture, so it looks a lot, it resembles a neural network. So, and better show you the graph. So this is what a neural network looks like. So you have some input data, then this input data is connected with some hidden layers, and the formula that connects the two, normally it looks like a regressor. So you have a set of betas and the constant value. Where we would like to get to is we want to replace this formula and we want to basically put any machine learning algorithm. So can we remove this regressor or perceptron and put any machine learning algorithm there? That's the basic idea. This is ideally how StackNet could be perceived. But how we would train such a network? So as you know, there are various ways to train neural network. A common one is to use backpropagation, but backpropagation requires the loss functions to be differentiable. If you don't know what this is, let's just ignore it for now. But this is not easily feasible if you want to put any machine learning model as an input. So we have to see another way to train these weights between the nodes, between the layers. So we could actually use stacking in order to form the connections between all the different nodes before we proceed to a new layer. However, we explained that stacking, the way it works, you need to have some training data in order then to be able to combine the different models. However, we did say that we are interested for a multi-layer architecture. So assuming that going beyond one level is useful, if we wanted to do this again, so not just to add a teacher, but also add a headmaster, we will basically split the validation data. And for every new layer, we will have to keep dividing our validation data because stacking requires unbiased estimates on some holdout data in order to find ways to combine different models. So you can see that this is not a good idea, especially when you don't have that much data. I mean, if you have to keep dividing, you will end up with, you know, really small data. So, and your model will not generalize well. So we use a different way to actually do this in Kaggle and within StackNet. It's a k-fold cross-validation to train this network. Consider the following data set. So again, we have a data set of x0, x1, x2, x3. These are our input variables, and we have a target variable where we try to predict. And if we set a k-fold where k equals 4, this 4 is a hyperparameter. So we decide what to put here. What this will do is it will divide our data set into 4 parts. And here I show you these 4 parts with different colors. It doesn't need to be sequential. It could have been shuffled. But I'm showing to you in a sequential way so that you can visualize it better. So what we're going to do next is we want to use a model and generate unbiased holdout predictions for this data set. We're going to create an empty vector of predictions. This is where we're going to put our predictions. And now we will start this process starting from 1, and we will use a subset of the data to train the model and another subset to make predictions for. In this case, let's say I will use the red, and I will make predictions for the blue part. Then I'm going to take these predictions for the blue part and put them into this prediction vector in the corresponding locations of these rows in the original data set. These are the first 2 rows. Now I'm going to repeat this. So I'm going in the second fold, I'm going to merge the blue, the yellow, and the green part and put them in the corresponding location in the prediction vector. And I'm going to do this again. We have generated holdout predictions in an unbiased way using the whole training data. So now we can use this whole vector of predictions. Once we have finished generating the training predictions, we can then use the whole training data, build one last model, and make predictions to, let's say, a test data set, if we have one. And now that we have training predictions and predictions for the test data, we can basically start the second algorithm. And we can repeat the same process. So this algorithm will be trained 4 times within the cross validations. It will populate this vector, and then we will use the whole training data to make predictions for the test. And we can keep doing this until we finish with one level. And then these predictions become the new training data set, and we basically repeat the same process. Now, many people tell me whether we need to change the seeds or change this k-fold cross validation every time we run this. Theoretically, it seems like a good strategy to do this. In practice, I have not seen it to matter that much. Also, a different way to generate predictions for the test data is, instead of building one last model in the end, using the whole training data, every time we make predictions for a validation data set, so each one of the 4 parts within the k-fold validation, we could have been scoring the test data set at the same time. And then we just take an average of these predictions. So that's a different way to generate predictions for the test data. I've seen that if you use neural networks, the method where you make 4 different predictions to the test data seems to be better. When you actually use tree-based methods like random forest, refitting on the whole data, and then making predictions on the test seems to perform a bit better. This is just based on my experience, but this is the technique we use to combine models. So this is how we generate the predictions of the different models. Explain to you how we can use this k-fold paradigm, this k-fold cross-validation, in order to generate training and test predictions, where then we can carry them into later layers. Now, another thing that we should point out is that neural networks normally are trained in epochs. So they have different iterations where the weights get recalibrated. So the weights kept changing until you reach a better solution. The way StackNet works is that every model gets trained immediately with the target variable, and this connection does not really change. However, a good way to recalibrate the models so as to make certain that you have the chance to revisit informations that may be lost in the original layers is to do a different sort of connecting among the different neurons. So the first connection I'm showing you is the typical one, where each teacher makes a prediction looking only at the students. So looks only at the previous layer. So the headmaster will only base predictions based on the teachers. A different way to do this is a mode called restacking, where the headmaster can actually take the predictions of the teachers and the students, and even have access to the original question. Surprisingly, this can work quite well, especially when you haven't built many models and you haven't exhausted all the information within your training data. So actually reappending, restacking the initial data or the first layer model's predictions can actually help you get better test predictions. So this is a good way to sort of have the chance to revisit any information that might have been ignored from the base models. That was the methodology about StackNet, or of this, let's say, multi-layer stacking. There is also a software where you can use in order to generate all this framework, and it is built in Java. Now, there is a big argument about why Java, why not in Python or R. First of all, StackNet includes its own algorithms, so algorithms that have been written from scratch. And even when you run something in Python, the underlying implementation is most probably not in Python, is, let's say, in C. So in that sense, I had to pick a language which is quite good for coding machine learning models. It could have been C, but C is a bit, well, it's a bit too verbose. At least it was for me. So I decided to go for Java, which is a very decent language, and it's good for making development of machine learning algorithms, like from scratch. I mean, it's not as verbose as C. It's extremely popular. It can be found in any operational system. The fact that it's statically typed just means that it's good. It helps you to avoid errors when you program, when you do the programming, and that's quite good because my code can be quite messy. Another inspiration for doing it in Java is because I felt there could be more impact, because Python does have something like scikit-learn, where there is a unified notation about how to apply machine learning methods. And when I initially made StackNet, I also saw it as a library where anyone could pick a machine learning model and run it completely separately from StackNet. So just if you wanted just to work in Java, you load the dataset, you do some validation, you can do some data preprocessing, and I have built methods for this. It's not as known as the actual StackNet implementation, but this was part of the inspiration. I felt that more people, this could affect more people when I first made this in Java. So initially, I built some algorithms from scratch. So and it includes some known implementations. For example, logistic regression also includes the liblinear implementation, for example. But then once I finished this, I started adding all these well-known models. You know, those models that in principle perform quite well. You know, they have won machine learning challenges. They're very respectable in the field. And yeah, that was the. I'm still in that second stage right now, where I try to make certain that if there's a machine learning algorithm you like, it is available, because it does matter to have all the tools available in order to be able to make strong StackNets, you know, strong meta-modeling frameworks. So StackNet can be used from the command line. It has commands, which we will see a few of them. I think the most important thing, though, is the params command. The params command expects a file, normally a txt, where it specifies the meta-modeling architecture. I'm giving you a sample here where you can see there are 3 base level models: a logistic regression, a gradient boosting model, and a random forest model, and 1 meta model. We can almost see this as there is 3 students and 1 teacher. Every algorithm has its own hyperparameters. Here, for example, you can see the random forest says estimators, which is the number of trees, maximum depth. We will go through this, or how you can interpret, how you can find which hyperparameters are associated with each algorithm later on. It's just the main point here is this is what the parameters file looks like. And if we, it will look like that. So initially, we call this jar file, StackNet, and the only prerequisite is actually to have Java installed. Then you say if you are running a classification or a regression problem. This is your task command. Then you specify the state of your input data, which it can be either sparse or dense. We will look about, we will see the difference of these two types later on. Then we specified a model parameter. So any model we've built, it's going to be saved here. So if we later just want to predict to some other data, we don't need to do this again. We just need to load this model. Then we specify the predictions file. So where we want predictions to be made. We specify the name of our training file. If we have a test file, we specify the name of the test file. Then we specify this parameters file I mentioned before, which is just a txt file that contains the structure you see on the bottom. Then we say if we want the algorithm to print stuff about the progress, how many models we want to run in parallel, that's the thread command, which metric we want to minimize or to maximize, or to monitor in general. And now what the input data looks like if you use the sparse command. So if sparse equals true, this is the SVM light format, if you're familiar. Where then you have space, and you choose column index and then value. Now this format is actually very useful because it saves lots of memory. What you basically say here is, I don't want you to tell me which columns in a row are 0. I want you to omit this. I want you to tell me every column that is not 0. For example, if you see at the top left where it says 32 column 1, what this means is that the column 32 has the value of 1, and you can assume that columns between 1 and 32 are 0. This is a very good way in order to save memory, and generally you need to have that in mind. So sometimes in order to make the most out of an algorithm, you need to find the right format. And in most cases, the sparse format is the best. You know, it just makes very good use of memory. Now I will briefly show you more like point to an example for a known. It was a very popular Kaggle competition. It was organized by Amazon. What was really interesting about this data set, it was the first I ever competed. It was in 2013. I think around 2,000 people participated. It was the first competition I ever entered. So it was quite competitive even back then. This had only 9 columns, this data set, and it wasn't very big. And you might actually think that 9 columns is not that much, but actually it is. There is a lot you could do with these 9 columns because they were all categorical and had very high cardinality. So thousands of unique values each column. So it was making it very difficult to extract the right information from these features. So it was around 9,000 rows, so not very big, but not very small either. So enough to get significant information. And yeah, basically Amazon wanted to predict whether a certain employee will require special accesses, like, for example, if they will need admin rights, and that's based on data like what is the role of the employee, in which department he's working. So, information about the employee and the role in general. And the metric that we had to optimize was area under the ROR curve. If you don't know what this is, let's just say is a score that tells us how good is the discrimination of our score, of our prediction versus whether an employee will require special accesses or not. You can find more details about the competition in the following links. And the main reason I said this is because I have an example using StackNet that can get you top 10 in this competition. And I think it's a very good place to start in general. It's a good way to start in Kaggle in general, but it's also a good way to start with StackNet. You can see this competition later on, and you can see what is the benefit of stacking. Let's look. Normally, this uses 2 different StackNets to get this top 10 score. I'm just going to show you only the first of the 2 StackNets because I think the other one gets a bit complicated and goes a bit beyond the scope of this presentation. Base models, mostly linear, and 1 meta model, so 1 teacher, which is a random forest. I did some pre-processing on the input data. So the pre-processing I did was I made everything as a dummy variable. So I used 1 hot encoding, and I also went up to 3-way interactions. So I created multiple interactions. So column 1 with column 2, let's say, and then column 1 with column 2 and column 3. So it was just to generate enough data to have diversity among my algorithms. And this is what the parameters file looks like: 9 base model, 1 meta model. What helps here is generally to have many models. Here I added 9 and 1. Most probably more models would give me a bit more. However, there is a plateauing after. There is a point where even if you add more models, you won't see much uplift. However, apart from the fact that you try to add many models, you need to make them diverse. So you need to make certain that each model makes different errors. Each model is able to seize the data from slightly different angles, because this way a meta model can explore where a model performs well and where it doesn't, and try to find models that at each point can perform best. And so it is important to make certain you have different models. So a rule that I tend to use is I try to make certain that I have models from various families. For example, some linear models like logistic regression or linear regression, some tree-based models like random forest, some gradient boosted models, some factorizations like libfm, support vector machines or neural networks. Because by default, they will seize the data slightly differently, and this will normally make the performance of a meta model better. Now, you also need to tune the hyperparameters, and this is a bit of a pain because it's not very straightforward. It's very difficult to know which parameters will be the right ones, and sometimes it's actually beneficial to put multiple models with different parameters, even if it is the same model. So logistic regression, which is, let's say, different regularization. Normally, this is a trial and error process. So you try different things and you see which one works best in cross-validation. In general, you need to try and find some parameters that make your model give some sensible results. It doesn't need to be perfect, but it shouldn't be very bad either in order to be useful. So in order to explain the results of this StackNet for this competition generated different predictions. So the best one was a logistic regression model, which gave an AUC of 0.893, and the worst one was actually the gradient boosting model with 0.85. As you can see, the predictions are quite different. Interestingly, if you were to average all these predictions, you would get a worse score in AUC, a lower score in AUC than the best single model, just because some models don't perform well, and this damages the average. However, a meta model can actually find when to use which model and is able to give a small uplift. So from 0.893 to 0.901 or 0.911 in the test data, and give you a very sizable uplift. You know, only this model could get you around top 50. If you were to average with the other StackNet dimension, you would get to the top 10. But this is the basic notion. This is the basic idea. So with the same input data, I was able to get this 0.08 uplift out of the box. You know, it's without, and this is how I perceive StackNet, to be honest. You have a data set, you would have gotten X in a given metric. Now you can get X plus something. That something may vary depending on different situations, but this is the basic idea. You can get more out of your input data, and the only thing you need to do is just tune the parameters a bit. So add different models and tune the parameters. Obviously, different architectures will work better, and this is a bit trial and error. But that's the basic idea. How do we find good parameters? I have two sections that hopefully can help a bit here. One way to do this is add the model where you try to optimize in your parameters file, and then add a second model. So using a space between the two models, so this break line defines the different layer. So here we have one student, the random forest, and one teacher, the logistic regression. It doesn't matter what you put as the meta model. So here I put logistic regression. I could have put anything else because we are not interested in performance of the meta model here. We only put this because StackNet expects at least 2 layers. We are only interested in that first model. And as soon as we can see the cross-validation predictions, we can stop this and rerun the process with different parameters. But let's see how this looks like. So I have these parameters files and I run StackNet. Then based on how many k-fold parameters we set, this will start giving the predictions for each one folds. So the cross-validation predictions. And we can see here that AUC in the first fold is 0.78. In the second fold, again, around 0.78. And so on. What I'm going to do next is I had random forest with max depth 5. Now I'm going to increase the maximum depth to 6. Now the AUC is improved from 0.78. Now it is 0.80. So I know this is a good change. And now I will keep doing this until there is no other improvement. And then once I finish with one parameter, which is the maximum depth, then I can move to other parameters. Let's say how many estimators I'm going to put, or how many cases I should have in a node. And once I'm done with the random forest model, I basically replace it with another one, let's say gradient boosting forest model, and I repeat the same process. So I try to tune this one. We can do it one at a time. And once I've built multiple like that, then I just put them together and run one final StackNet with everything inside. And this is how you can get the score. Normally, when I do this tuning process, I use a smaller file in order to make it quicker. Another way to find good parameters is actually, because I have experimented a lot with machine learning models, it would be fair to say that I have tuned more than 1,000 different machine learning models over my tenure in Kaggle and my professional career. So I think I've learned quite a few tricks, or which parameters at least are quite useful in different models. And I have added this in StackNet's main GitHub page. So somewhere in the main page, it will show all the algorithms that are contained. If you click on these algorithms, it will take and put it in your parameters file. And then you can also see which parameter it includes and also which ones are important. The ones that are important are flagged with the label, this is important. Normally it is at the end of the sentence that describes one parameter. So I have done quite some work, and this at least can save you some time. I mean, if you have time, you can explore other parameters too, but normally these parameters should get you there, should get you to a good performance. And even if you don't want to use this within StackNet, for example, I have included the same section for, let's say, XGBoost. You can use this in order to learn which parameters are important and apply it even outside StackNet. You know, you can use it as a reference. I think it works quite well. So some more tips. What is really important, I mentioned before, apart from performance, is to generate diversity between your algorithms. So to make certain that your algorithms sees the data from different angles, they don't need to be perfect, they just need to be making slightly different predictions. A good way to do this, as I mentioned before, is based on the input structure you have. So something that I do and tends to work quite well is to include 2 or 3 gradient boosted trees, like XGBoost, for example, or like GBM, where the way I make them diverse is by setting different maximum depth levels. For example, I will make one with small depth, one with medium depth, and one with high depth. Let's say small is 4, medium is around 7 or 8, high is around 10, 11, 12, something like that. So this is how I generate diversity. I know that not all of them will perform really well, but they will give me slightly different predictions, and the meta model will probably benefit from it. I do the same with neural networks. So I try to do one with 1 hidden layer, one with 2 hidden layers, and one a bit deeper with 3 hidden layers. Again, the main idea is to generate diversity. I do 1 or 2 random forests. I try to build a few linear models too. K nearest neighbor models actually help me quite a lot. And this is a good example of a model that normally doesn't perform very competitively against the other models. For example, let's say the XGBoost models. But in most situations, it adds in a meta model. You know, because I think it seizes the data quite differently, significantly different. And this can be leveraged by the meta model, and most of the times it yields good uplift. I also like factorization machines. A different way to generate diversity is with the kind of pre-processing you do in your input data. I don't want to go to that much detail here, but it's important. Sometimes it's important to do one single transformation in your data and then rerun StackNet. So run, let's say, the same architecture, just on a small different transformation of your input data. For example, once you transform your data using dummy variables or one-hot encoding, the other time you replace your categories with a number of counts or the frequency of the classes, so how many times they appear. You can do the same with the numerical features. You can try one StackNet where you remove outliers. You can try a StackNet where you bin the numerical features and you convert them to categoricals. You can try one where you do scaling and so on. And then you can also try to explore interactions, so column A with column B. You can try to create some aggregate measures, or you can even try some unsupervised learning techniques like principal components to generate some features. And all of these help to generate slightly different predictions, which they can be really, really good when you try to build a strong meta model. Now I'm going to show you a second example where I have also shared data, and you can run this yourself too if you want later. Which I think the data set is not very big, so it's ideal for this kind of. I'm showing you a dense representation of the data. This looks pretty much like any tabular data set. You have your target variable in the beginning, and then comma separated the values for the features. So this is, if you were to use, let's say, your data in Excel or in a standard CSV, this is what it would look like. This is the dense format. This is also quite useful, obviously, if you don't have that many zeros or missing values in your data. So in the example I've shared, you have a trained CSV and a CSV, so 10 features and the target variable in the beginning. And then where it shows you all the commands we're going to run in order to generate this, to make this experiment. So you basically just copy these values into a terminal, in the same terminal where you have StackNet and every other file, and it will basically run StackNet. I'll show you also later, but these commands is all you need basically. I need to point out that the version of StackNet I shared is a light version. It doesn't include, for example, XJBoost. That's because this is a bit more complicated to install. And in order to make certain that everyone can run this, I decided to exclude and have only the native algorithms inside. So the ones I've built myself. So look at the first one called params.txt. I only have two models. So I have a linear regression fit on the input data, and then another linear regression fit on the predictions of that first linear regressor. So one student and one teacher here. What you should note is the regularization parameter C I have highlighted, which is a penalty imposed in the coefficients of linear regression. And what you should know is that these parameters I've put are really bad. These are not good parameters for this problem, but I put this on purpose, just to show you what happens. I wanted to highlight the importance of generally having good parameters in your models. So if we run this in the same area where all these files are, and where the StackNet file is, the jar file, then at some point print you the average metric for the first model. So these are the cross-validation results, which is the average error is around 15 here. It will also give you the average error for the test data. As you can see, the error in the test data is still quite smaller, significantly smaller actually, than the error in the trained data. And that's because, if you see above, the regularization parameter in the second model is more suitable and is able to correct some of the errors of the first model and gives you some better results. So if we were to plot these predictions versus the actual Y variable in the target in the test data set, it will look like that. So you can see that actually the R square is quite high, and you can clearly see that the prediction irrespective of the error, which you can clearly see there is some error. But in principle, the prediction is well correlated with the actual target variable. So what will happen if we run this with better parameters? Better parameters here means smaller penalty, so smaller regularization. So if we were to use the params 0.txt file and rerun the same command, now the error drops to 0.44.8 for the training data, and around the same level for the test data. And let's see how this would look like in a graph if we were to plot that prediction with the y variable of the test data set. More like a line, you know, the average error is much smaller. Obviously, it's not a straight line yet. It's not a perfect prediction, but you can see how the prediction has improved just with finding better parameters here. And now we can try to expand on this and add one more student. So we can try and add one gradient boosting model, where you can also see it in the graphical representation underneath. And we run the same command, and you can see that the two models' predictions, although are quite close, you see one is 0.44, the linear model, the gradient boosting model is 0.42. However, the meta model is able to find a more optimal way to combine them and is able to drop the error to 0.33, which is a significant improvement. And let's see how does this look in a graphical representation. I'm doing it again. You see now is the prediction becomes more linearly related with the target. It becomes, that relationship becomes more like a straight line. And let's see what will happen if we try to add a neural network to this. So add a new student. The neural network performs very well. So the error is 0.24. And this is not surprising because I generated this data manually, and I generated using a neural network. So I'm not surprised that it does so much better than the rest for this problem. Thing is, we have three different models, and the meta model is able to combine these to drop the error to 0.17, which is significantly smaller than before. And let's see how this looks like. See, you are almost not able to see the line anymore. So the one that I drew in order to show you what a perfect relationship would look like. And the R squared is also very high now, 0.9986. Now I'll show you the importance of picking the right meta model. So it's not just about picking the right children, the right student in this scenario. If I change the linear regression of the meta model and put a random forest, input now drops to 0.16 from 0.17. You can see that the relationship is even more like a straight line now, apart a bit in the end. So in the end, there is still a bit of an error, where we can try to squeeze it by adding a new layer. Introduce a linear regressor again as a teacher, so as a meta model, and then I also introduce a higher level model, a third layer in this case, which is another linear regression, and I was able to drop the error from 0.16 to 0.15 by adding this new layer. And you can see that the error at the end of the line is further reduced. You can see it again. And I show you how, with picking different parameters, different input models, different meta models, and even adding more layers, we are able to get better prediction. Yes, marginally, the predictions are less significant, obviously, in every new layer, but it's still a way to squeeze more information about your target variable. Here I list a few resources where you might find useful, which is just the main GitHub repository. It contains, I think, lots of information. There is now a Facebook page too, I made dedicated for StackNet and open source tools in general, like H2O. If you search StackNet examples in Google, you will find a few mostly related with Kaggle, but there's obviously the main GitHub page too. There is a blog about StackNet where it explains some things a bit more, let's say, in an easy manner, where you might consider it was in Kaggle. If you want more information about stacking and another software that can do this, then I also would like to recommend you look at H2O documentation, because they have done actually some work around this area. So you should definitely have a look. You know, they also explain some things much better than I do. And there's some blogs that, you know, I've used StackNet to win competitions, and you can have a look too if you want. Let's ignore this, just StackNet architecture used to win this data competition just from a different angle. And that's basically the end of my presentation. I guess before I show you, before you ask me any questions, let me just show you a bit